last year you were only given the type of Lewis structures that we just covered in the previous video, which are ones that obey the octet rule, with the exception of maybe boron trifluoride or something like that. We had we asked you to learn the exceptions: boron, beryllium, and hydrogen, basically. This year, however, you're given slightly tougher ones. We've got 3 typical ones up here: NO2, PCl5, and IF3. Now, those last 2 automatically scream out to you that they must have something funny happening, because there's 5 things bound to a central atom. So how could that be the octet rule? If a bond is a paired electron, then they must have at least 10 electrons around the central atom. And basically it's because the d orbital is being involved in bonding in these cases. And you've got things like hybrid orbitals and all that. You don't need to know the why, you just need to be aware that the central atom can sometimes break the octet rule. NO2 is quite a cool one, because NO2, which is a brown poisonous gas, is in a natural equilibrium with N2O4, which is a colourless gas, which isn't quite so bad for you. The reason for that equilibrium becomes really obvious when we do the Lewis structure for it. So again, we're going to go through the same rules, that nitrogen has got 5 and oxygen's got 6. So we're going to look at our total number of electrons. The other giveaway is the odd number we're going to get here. So here we've got 5, because if you want to use the Bohr model, 2, 5, plus 2 times 6. So we've got 17 electrons. So that sort of screams to us we've got a problem anyway, because you're going to have an odd number around one of them. Again, just like before, we're going to go N with an O, and then fill in maybe these, and see how many we've got. 2, 4, 6, 8, 10, 12, 14, 16. 1 left, so we'll put on the nitrogen. Still not really enough around that, so we're going to move one of these to make a double bond. And you'll notice the nitrogen's still only got 7, so what do? Well, I could put another double bond in there so it goes up to 9, but actually nitrogen doesn't have the ability to do that. So nitrogen's a bit special in that it can have 7 or it can have 8. Okay? So that is actually correct for nitrogen dioxide. A single bond to an oxygen, a double bond to an oxygen, and a lone electron, not a lone pair, just a lone one. This year, I believe nitrogen is the only one you'll meet that does this. Okay, so if you've got nitrogen and you get an odd number for your sum of electrons, don't be surprised if your nitrogen has only got 7 electrons around it. Okay, 1, 2, 3, 4, 5, 6, 7. Okay, so that's nitrogen being a special case. Phosphorus is one that can actually have up to 10. And in this case, that's exactly what it's going to do. So phosphorus being 5, and we've got 5 times, 5 times 7. So we're going to have a total of 40 electrons here. Alright, if I was just to start by having phosphorus with 5 chemical bonds with them as far away from each other as I can to chlorine, and then, bear with me, I'm going to use dots this time, 2, 4, 6, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, which is what I had to get. So you can see why I did dots, not crosses, I hope. Yep. Sorry if that doesn't come up in the video. This is the correct structure for phosphorus pentachloride. Now when we get to it later, we're going to have to know the shape of that. It is a symmetrical shape because all of those bonds are identical and there's no lone pairs around the phosphorus. So that is correct, that one there. Alright, so some things can break it, but only the central atom is breaking the octet rule, not the outside ones. Okay. Next one, iodine pentafluoride. Okay, it's going to look like that, isn't it? Basically. One thing you have to be careful of. Iodine's got 7 valence electrons, so this is going to have 2 more electrons. It's going to have 42 electrons. So if I was to do the same thing as my phosphorus pentachloride, makes sense, 1 central atom, 5 around it, have a look at what happens. We'll see, it's terrible. Here we go. Okay, if I do that, I've only got 40 electrons. So now I've got this decision. Where am I going to put the other 2? Well, my outside ones are not allowed to break the octet rule, so I've only got one place left. So I put them with the iodine. Okay. So this is going to be a different shape to this, and actually a different polarity, because with this lone pair, it's going to make it an asymmetrical shape. It's going to change its geometry. This is now the correct one for IF5. Okay. Just for your information, that's a square-based pyramid. These 4 basically make a square, and then this one is sticking straight out of the board at you. Okay? Roughly, that's the shape. With the lone pair below the iodine, pushing everything away from it. Okay? This one here is going to have a triangle. It's going to be basically a triangle that's got one at the bottom and one at the top. Okay? So it's basically a trigonal bipyramid. So that's the shape you'd see with that one. Again, geometric, so it can be folded in a few different symmetrical, can be folded in a few different ways. So just be aware that the octet rule can be broken by a central atom. Sometimes it's got fewer electrons. Hydrogen's not essential, but boron, beryllium, they're good examples of that. And nitrogen is really funky. It only can actually be stable with only 7, as long as it's the central atom. Sometimes you can exceed the octet rule with the central atom. Usually it's things that have got high enough energy level electrons that they can have bonding in the d orbital, okay, or in hybrid orbitals between those. Again, the reason, not important, as long as you know it's central atoms only, and it's good to do lots of practice. I'll stop this one there before we get into iron.